spatiotemporal modeling and a bit about parameter estimation. So the talk will be in in two parts. It will literally be in two parts. I'm going to switch slides to another set. That's slightly my laziness. The one that's first is in Keynote, the second's in PDF. So couldn't merge them. And if yes, this is a Lancaster double bill. I think this week we have Lancaster on Thursday. Stefan's talking. And then if that wasn't enough pressure as well, then there's a live feed, right? And I sent the link to my dad. He's a professor in computational electromagnetics, and he'll be following this. And let's see if he thinks his investment in my application has yielded a return or not.
He's already given me some questions to ask.
All right. Yeah. So my collaborators are a mixture of oceanographers and statisticians. So oceanography will be the application I'll talk about today. So Jonathan and Jeffrey, based in Seattle, where I spent 2.5 very happy years, and then Sophia and Arthur, who were in UCL. So today we're going to be talking about this idea of particle trajectories. So we've got data everywhere, as we know, but some of it's also moving. And that might be a wearable device you wear to go running, cycling, record your trajectory. It could be recordings of traffic flow. It could be, in this case, there's a lot happening now with accelerometers being placed on animals, whether that's birds or underwater creatures or land mammals and so on. And also the ocean. So here's an old-fashioned way of doing it in the ocean is you throw a message in a bottle and you see where it goes. And so it's the lowest tech, I guess, of the options there. But it's surprising in the ocean how we have a lot of technology to observe the ocean, satellites, ships, underwater vehicles, but still throwing something in and seeing where it goes is still one of the best ways of understanding the ocean. And actually some of the best earliest measurements come from things that effectively are messages in a bottle or cargo that was accidentally lost at sea, and then they see where it washes up and so on. But let's take that last one up, and that's what they've been doing now for 40 years. So this we could call what we call a drifter. It's a high-tech version of the message in the bottle. And the idea is that somebody goes out, throws it out at sea, and it consists of a surface buoy, which is that sort of spherical object you see at the top, a subsurface drogue, which is attached by a thin tether, and the whole thing sort of stretches out. So we see the drifter or the float at the top, a tether, and this is called a drogue, sometimes called a holy sock as well, because it's got holes in it. And the idea is that this creates the right kind of drag to stop the top float just being blown around by water, but actually sort of makes it mimic a particle or a parcel of water. So that's the idea of that instrument there. And then inside the float at the top, you have all sorts of fancy communication devices which communicate to passing satellites.
So when you said blown by water, do you mean blown by wind?
Wind, yeah. Did I say water?
You said water.
Yeah. Stops it from being blown by wind, makes it more like a particle of water. And the measurements it transmits include its locations, from which we can infer surface velocities, but also things like temperature, wind, pressure, salinity, ocean color, so we get some multivariate statistics. And this program is run by NOAA and the Atlantic Oceanographic and Meteorological Laboratory in Miami, so it's just some obligatory things there. So, what does the data look like? Well, the Global Drifter program has actually been running since 1979. In this animation, we'll see some data from 1980 onwards. It's going to be a video. The program first started in the equatorial Pacific, and what we see in this animation will slowly sort of populate are the trajectories that these drifters have been making at the surface of the ocean. The color represents speed, so if it's red, it's going more quickly. And what we can see, what's the pointer here, is first of all, over time we get more data as more and more instruments have been deployed around the globe. We can see some of the currents appearing along the equator. The Gulf Stream's pretty visible. There's a similar Kuroshio current of Japan, and you'll see one forming around South Africa called the Agulhas as well, and the Antarctic circumpolar current. So things tend to go all the way around the globe in one direction there. Here's the status as of last week. So at the moment there are 1,400 out there, in total 20,000 have been deployed. And the colour here represents the deploying country, so you sort of see it's a global effort here. And I'm not going to talk much about this data today, just a little bit. It's more sort of a motivation for the research, but if you're interested in how to download it, how it's pre-processed and so on, and there's details in this paper, which is the latest product, which is interpolated at hourly resolution. So you get data from each instrument every hour. As they've increased the number of satellites, we can achieve that now. So the first thing you might do with a database like this is just plot it all at once. Call it like a data dump, if you like, and sort of look at it and be like, okay, what do we actually do next? What you see here, each squiggly line is the trajectory of one of these drifters. And this is affectionately known in oceanography as a spaghetti plot. So
what do you do when a drifter washes up on a beach?
It'll be collected, often, if they can access it. Or if not, then these days they're all kind of biodegradable and stuff, so you just leave it to die.
And the colors of the were there starting points?
No, actually the colours hidden, I apologise, don't mean anything. That's just MATLAB going through a loop. Yeah. Sorry to disappoint them. The first thing we might try and do with a data set like this is we look at that and say, okay, that's a lot of data, we can't figure out what's going on, let's average it. So if we average it, we can get the mean speeds through each geographical bin. So I've just taken 1 degree bins here and just averaged the speed the drifter goes through. And that's already quite informative, and this is actually a pretty useful map. We see the major currents coming out and the more sort of quiescent regions in the ocean as well. But as we know, averaging is a waste as statisticians. So the idea in this talk is how do we get about modelling more structure than just the mean speed. And now we're going to go into the second order structure to try and describe the variability in the data. But one of the challenging things about this data, as I said in my first slide, is that it's moving. It's not just fixed location measurements in space over time, but it's data that's moving in space and time. So one of the questions we need to ask is, well, what's our actual frame of reference here? And here there's a choice that physicists often have to make, and now as statisticians we do if we want to look at this data. So one comes from Euler and the other from Lagrange. So in an Eulerian reference, we'd observe a fluid through a fixed spatial location over time. So if you imagine whether it's a fluid data or the other data I talked about at the beginning, let's say it's people running a marathon, and you stand at one point and watch everyone coming through, and you record that data. That would be an Eulerian frame. The other would be a Lagrangian frame, which is the observer actually follows the fluid parcel as it moves through time, space and time. So there, if it's a runner, you actually look at the data from that specific run as he completes the marathon. Or in the fluid case, you follow the instrument and look at its measurements. And there's sort of this choice you have to make. And here we're going to talk about the Lagrangian reference frame and why that's a good one, we think, for analysing the drifter data. And the reason is that we can look at data from a single trajectory and model all of its dependence locally in space and time, rather than having to wait for another drifter to go through the same spot, which could take a long time. So here's one drifter trajectory of a North Atlantic drifter. The red and the green are highlighted for later analysis. They're just segments. So I think it started here, and we see a lot of features here. So here we just see a sort of drift. Here we see a lot of turbulence and eddies. things mixing and swirling around, lots of different oscillations, and then it comes out here. And the reason why this is particularly interesting and energetic is that it's near, this is just off the coast of North Carolina, which is close to the jet stream, which gives us our warm waters that we have here, given our altitude. So, from this red trajectory, that's the segment of the previous trajectory, what we can do is we can separate out and look at its velocities in the eastward and northward direction, sometimes called zonal and meridional, and we're just going to call them U and V in centimeters per second here, and this is time here. So this is just a time series. So I've taken a spatial temporal trajectory and just turned it into two time series, and then we're going to represent that as a complex value time series. We could do it as a bivariate. It doesn't mathematically make any difference. It's just for convenience here. We're going to have z equals ut equals I vt. So what we've done is we've turned a spatial temporal trajectory into one time series. But we also are going to retain the information of its location and stamp that outside. So you could model this as a joint spatial temporal equation, like SPDE, for example, but we're not going to do that. We're going to stick to time series modeling and just stamp the spatial information on the outside and analyze that later. So we have this object Z now, which is our velocity time series for one drifter, and we can look at its power spectral density. And if we do that, we see two peaks here. So actually, what might look like just one oscillation here, there are actually two in here. The big one here is this big one that we see, but there's also a counter-rotation happening here, close to the Coriolis frequency. So that's the effect of the Earth spinning on its own axis. It's creating a second oscillation, which is barely visible here. And then if we look at the green one, then we actually see this peak at the Coriolis frequency be much larger, almost as big as this one here. And that's actually this oscillation in here. So this green one is actually rotating the other direction to the red one, despite being very close to each other. And this is the effect of the Earth's rotation on its own axis. So the previous one was a local effect. That's an eddy. This is actually something that comes from a global phenomenon of the Coriolis effect. And with looking at the spectral densities, we can separate those things. But to go further than that, to go from non-parametrics, we want to bring in the physics, and we're going to actually build a parametric model. And I'm just going to quickly go over the slide because I really want to get into the anisotropy. But here's an initial isotropic model. So we're going to model oscillations. Inertial oscillations are the ones created by the Coriolis effect, and also tides, as complex valued Ornstein-Uhlenbeck processes, which has the following stochastic differential equation. So we've got Z, our velocity here, given by what would be a standard OU, plus we have the additional I F naught, which you may have not seen before, and that creates an oscillation. So we have, this is the regular damping term in an OU, this is the regular forcing term with Brownian increments, and then we have this oscillation here. So it's a 3-parameter model, which gives us stochastic oscillations. And this is actually, we simply picked this because it's the stochastic analog of a well-known model in physical oceanography, which is deterministic, and we just took a stochastic analog. But then, and then it has a power spectral density, so I omitted that part, which gives us this off-zero peak that we were observing in the data, located at F naught. Now for the background flow, that was all the large peak near zero. We're going to model this as a Matern process. It doesn't admit an SDE because it's a fractional process. But its power spectral density is nice and analytic, and it's very similar to the OU, except our peak's going to be located at zero, but we're going to also have an additional alpha term, which gives us a rate of decay for spectral density. And what that actually does, as many of you who have worked with the Matern process will know, is it controls the roughness or smoothness of the process. And this turns out to be really useful in the context of modeling turbulence. Some more details on this model are in this paper. And just to illustrate that,
I was just curious, your A coefficients, they are not time dependent, so they stay the same, the one where you scale your Brownian?
we assume all coefficients are locally stationary. So we estimate them locally stationary in space and time. So we estimate them in some window, but we let them evolve.
So they could change, but on average, and A0 is describing, I guess, the average. Is that what's happening?
That what, sorry?
And your coefficient A0.
We let them all change. The amplitude changes too. You'll see some plots later of that. So what we see here is a numerical model of turbulence. This isn't real data. This is a complicated deterministic model, a bit like Navier-Stokes. It's called quasi-geostrophic turbulence. And that's what's happening in the background here. And what we've done is we've thrown a bunch of synthetic drifters in. That's what the black dots are, and their colours. Colours don't mean anything, I'm sorry, Ed. There's just to distinguish them, the colours are their most recent trajectory. And what I'm going to do in the next slide is see if the Matern process could actually model the movement of these drifters through this turbulence. So what I'm going to do is I'm going to take all the drifters and suppose they started in the same location. And that's what you see on the left here. So it's the same data, it's just I fixed the initial positions to be the same. And you see this sort of diffusion that happens here on the left. And what the area represents is the mean square distance from the origin of all of the black dots over time. And here we fitted a Matern process with just one choice of parameter, of each parameter, and simulated an identical number of trajectories. And you can see a nice visual similarity. And what's similar between them is a number of things. One is sort of the general scaling behavior. The amplitude is about the same, but also the smoothness of the trajectories. And that's what we can control with the Matern. So we can make these things rougher or smoother by changing that alpha parameter. So we've matched it to match the smoothness of these trajectories. And the final thing is this circle. So this circle gives you the rate. This circle gives you characteristics about the dispersion. And what we see here is that the circle is actually growing linearly in time in terms of its area, not its radius. So its radius goes at the square root of time. Its area grows linearly in time. And that's characteristic of what we call a diffusive process. And that rate of growth is called the diffusivity. And we can match that too in the Matern. We also get, theoretically, this area growing linearly in time. And we can estimate what the diffusivity is, that rate of growth. And more details on this model and why it's a good model for capturing turbulence in the ocean in a separate paper. So how does it look fitting to the real data? So here I've taken the green trajectory, plotted you the velocity spectrum of the velocities from here. The negative and positive frequencies are because it's complex, so we have different directions of oscillation. And the green line is the fit of our model that I presented earlier with the complex Ornstein-Uhlenbeck here and the Matern here. And we just fit to these frequencies. We're actually being semi-parametric. We exclude high frequencies because here we have interpolation artifacts which we want to ignore. And we just model the one side of the spectrum where the energy mainly is. We're going to model the other side when we look at anisotropy. So more on that in about 5 minutes. And then fitting it to the red data, we see a similarly good fit, but this interesting difference that's occurring between the Coriolis frequency here and the peak here. And this peak is actually the same difference as the difference between this peak and 0. So this distance is the same as this distance. And this was actually hypothesized but never observed in a 1980s thesis. And here we've been able to spot it. And now we can use our model and machine learning techniques and so on to actually spot this in the ocean where this occurs. So now I think is a good time to pause and say, wait, why are we actually doing all of this? Sometimes a question I get, and I'm like, well, it's fun, right? But actually it turns out it's also useful. So here we see a spaghetti plot. This is drifters in the Gulf Stream. What could this be useful for? Well, one thing you may have thought when you saw those drifters spreading is oil spill spreads. So this has been of interest motivated by the Deepwater Horizon oil spill, that we can use the idea of these drifters spreading to better understand how an oil spill might spread. Another one is climate change, and the ocean is recognized as being one of the key drivers of climate change. And the reason for that is transport. The ability of the ocean to move these distances, move water these distances, transports heat from the tropics to the poles and ocean circulation, as we know. So a better understanding of this behavior gives us a better understanding of climate change. And finally, transport of other objects in the ocean. Here I've got plankton, but it could also be non-living objects like plastics or debris from ships and planes and so on. And this data has been used to sort of try and better understand the movement of other objects in the ocean. Right. So motivated by this, we've done a global analysis. So we've done a few, but I'm just going to present results from a high resolution data set which goes back to 2004. In this case, we have 73 million data points, irregular temporal sampling with a median sampling interval of 1.22 hours. And here we see the data density. So this is just the density in different parts of the ocean. We see we have this slight inhomogeneity issue where we have more data in the North Atlantic, and we have these sort of black holes, like things don't really like to go across the equator, and obviously not much towards the poles. But nonetheless, we fit the data, we fit the model I presented, and we let the parameters, as Stefan was asking, we let them vary, and we just fit them locally in space and time at different locations. And here's what we get. For example, this is the diffusivity, kappa, which comes from the Matern process. It's the rate of growth of that circle. And now we can see that it varies quite wildly across the ocean. So there are areas like in the Gulf Stream where things will diffuse more quickly. In the quieter areas of the ocean, like the North Pacific, things will diffuse slowly. Another one that's been of particular interest is the idea of this slope parameter alpha, which gives us the roughness or smoothness of the trajectories. So no one's really estimated this from real data before, and we're the first people to construct this global map of how roughness or smoothness changes in these trajectories. Typical slope parameter is 1, which is equivalent, so that's alpha equals 1, is equivalent to saying the velocities are like an Ornstein-Uhlenbeck process, or like a Brownian motion. So the trajectories themselves are like an integrated Brownian motion, or an integrated OU. But we see areas where, over strong currents, where the alpha parameter here is much bigger, it goes as high as 2 or 2.5. So we get these much smoother trajectories along the major currents, as we'd expect. So rather than things having a certain roughness, when they hit the Gulf Stream, they go off in a straight line. And that's what we can spot here with this higher alpha value. So that's the end of that part of the talk, because I want to sort of present some newer work where we've looked at anisotropy. So far everything I've assumed isotropic. That was a circle growing in space and time. But in reality, especially near boundaries, we wouldn't expect things to be purely isotropic. So first let's look at some numerical modeling. So here's an anisotropic experiment of anisotropic turbulence, something which we call the beta plane. So now the previous simulation I showed you of numerical fluids with the turbulence was done on what's called an F-plane, which is like a flat Earth scenario. But a beta plane is when you consider a rotating spherical surface. So it's the Earth, basically. In fact, in this simulation, Jeffrey made, to exaggerate this beta plane effect, he made the planet a bit bigger. So it's about the size of Jupiter in this experiment. And that's why this looks like Jupiter. So if you've observed Jupiter's atmosphere, you'll see you have these strong east-west jets that form. You can see them here as well. So the idea is that there's a propensity for things to move east-west much more than north-south. And that's created by the rotation of this giant object. And this here is an Eulerian spectrum. It's the eddy kinetic energy. This is wave number, not frequency. So this is a spatial spectrum. And what we see are sort of these multi-scale effects, different power law behaviors. This one's really more for the physicists. But if you focus on these two plots, these are drifters or floats moving, and this is what we call vorticity. So it's, anyone who's done a fluids course will know about that. So if we follow the same methodology as before, and we look at some time series, here's the velocities for one particle trajectory. U is your eastward, V is your northward, and you see that you have a lot more energy going in U than you do in V. We're going to take the same step as before, represent it as a complex value time series. Nothing's different. But now if we look at the power spectrum, then actually it looks fine. I fitted an isotropic Matern to a multi-tapered spectral estimate, and the fits look pretty good everywhere. So what's gone wrong here? Well, we actually need to look at U and V separately. So if I fit an isotropic Matern to U, then we see that there's a bit of an underestimate in the model versus the data. Here, recording this is on a log scale, and an overestimate in V, which becomes more apparent. So here in V, we're seeing that the isotropic Matern is not a good fit to the time series in V, but it is to U. So, but interestingly, it's a good fit at some frequencies, and there's this dip. So what we don't want to do is just squish a Matern in one direction and stretch it in the other, because actually it looks isotropic at high frequencies. It's just at low frequencies here where it appears anisotropic, where there's more in U than in V.
It looks very symmetric.
Yes, that's a good point. In general, it wouldn't be, yeah. So I guess this is, what that means is that there's an equal amount rotating in one direction as in the other, in terms of the split in
Could you
energy.
go back to the U just to see what U looked like?
Yeah. It's a good spot. So the next 10 minutes of the talk will be about how can we capture this difference between U and V. And to do that, we're actually going to follow some signal processing literature. We're going to look at something called the rotary components. What the rotary components do, they're called Z plus and Z minus, is they decompose ZT by direction of spin. So it's those two sides of the spectrum. So Z plus contains the positive frequencies only, and Z minus contains just the negative frequencies, and then you can reconstruct the signal from these components. They're sometimes called the analytic and anti-analytic signal as well. And the rotary spectra are just going to be denoted S++ and S-. And the key to capturing anisotropy is going to be to look at the rotary cross spectrum. So it's the cross spectrum between Z plus and Z minus. So the dependency structure in frequency space between these two objects. So how the two sides of the spectrum are correlated. And we're going to denote that S plus minus. And the reason for that is that lets us separate signals that are circular versus non-circular. So this is jargon from the signal processing literature. So when a signal is circular, then it has a formal definition, which is that the complementary covariance, which is different to the autocovariance, is 0 at all x. But let's not dwell on that, because conveniently, this is equivalent to this object I just described, the rotary cross spectrum, which should be 0 for all omega in the rotary case. So what that means is we can look at this object to spot if something is circular or non-circular. So a circular signal can also be called proper in some literature, and if Z is looking at spatial data, isotropic, and that's the key thing here. A non-circular signal can also be called improper or anisotropic. conversely. And I think that's a peculiarity of the English language, that the opposite of circular is non-circular, proper is improper, and isotropic is anisotropic. It's different every time. And the idea is, if we want to spot anisotropy, we can borrow these ideas from the signal processing literature, that we're looking for signals that are non-circular. So how might we model non-circularity? Well, that comes from the rotary cross spectrum, S plus minus. We're going to normalize that by the spectral densities in plus and minus, square rooted, to get a rotary coherency, just like a regular coherency in bivariate time series analysis. It's going to be complex in general, with an amplitude and a phase. And in a paper last year, we proposed a general class of models to model this rotary coherence. For example, here we can just have sort of this polynomial type model up to a certain frequency, and then we let it be 0 above that. And that's what we employ here for our turbulence simulation. So here we've got the snapshots of an anisotropic experiment, the sort of Jupiter style thing that I showed before, and this is isotropic, just as comparison. This is a sort of flat Earth style scenario. So if we go back to looking at those velocities, we had that difference between u and v. And if we look at the rotary coherence of that same signal, what we see, it's a bit noisy, but at low frequencies, the coherency is 1, and then it seems to decay to 0 and be very noisy, more or less around 0 there. And what the model that we build, an anisotropic return, is to fit this triangle kernel here, where we just need to determine one parameter, the location of this hinge, if you like, which can move anywhere from low to high frequency. And that then becomes the anisotropic timescale. So the idea is that anything below this frequency is anisotropic, anything above this frequency is isotropic. And now if we fit that to our spectral densities, then this is what we had before. Everything looks great in Z, but if we look at U, sorry if the color's not that clear, but we can now get this extra bump at low frequencies with the addition of one parameter to form this anisotropic return, and we can more or less capture the dip occurring here in V. So we've gone from 3 parameters to 4 parameters, and this 4th parameter gives us anisotropy. From that we can do all sorts of useful things. We can, for example, test for anisotropy. So here's just a likelihood ratio test with the anisotropic and isotropic data with a 95% confidence interval. And we can sort of separate these out and spot the anisotropic data. And also we can measure this time scale, that location that I showed you on the spectrum, where anisotropy begins. And here's a histogram of those. They are quite spread, but the median actually agrees quite nicely with something called the Rhine scale in physics. So there was sort of a physical result coming out of this analysis. And just so you can see a similar style animation to before, but now with anisotropy, on the top we have the numerical model, and here we have a stochastic model from the return, and again we get this visual similarity. But the idea is if we zoomed in here, it would look isotropic. It's only as we zoom out that it becomes anisotropic. So it's not just a stretching of a regular return. It's got that key ingredient that I discussed there. So that's the first part of the talk, which is the longer part. And this is the part where I switch slides. I guess I should just take questions at the end, Richard, or yeah. So this part's going to be in it's on the wrong. There it is. The last part of the talk, which should only take 10 minutes or so, is to do with parameter estimation. So I've talked a lot about modeling, but how have we actually estimated all these parameters from the data and made it work for a giant data set. So it's going to be about estimating these time series parameters in the frequency domain, how we can be both computationally efficient and unbiased. So the motivation is as such. suppose we observe just a single length n time series x from a second order stationary stochastic process, x continuous time t, parameter vector theta. How do we estimate theta? Well, we can resort to maximum likelihood, which is great, but it's computationally slow. And we found it too slow for these 100 million data points that we had in the global drifter program. You could use method of moments, faster, but usually biased and higher variance in comparison. And then there's this in-between space that has had a lot of attention in the last 10 years or so, which are quasi and pseudo-likelihoods. People have been doing this in the time domain, using tricks such as circular embedding, such as in this paper, or actually frequency domain ideas go all the way back to Whittle in 1953 with the Whittle likelihood. And the idea is that these methods are what are called n log n methods. So maximum likelihood would be n squared or n cubed, dependent on the structure of your covariance matrix. This is much faster, n log n. So if you're using millions of data points, then it'll run much more quickly. In this part of the talk, we're going to discuss how we can improve the performance of the Whittle likelihood, because we found that it needed improvement for the data set we were looking at, and that motivated a new method. So for a regularly sampled time series with sampling interval delta, just some necessary definitions. I think there's just three in total. So we've got the autocovariance, which you're probably all familiar with, which we're just going to call lowercase s at lag tau. We've got the power spectral density, which we're just going to define to be a Fourier pair with our autocovariance. So that's going to be lowercase f at frequency omega. And then we've got the periodogram, which we can estimate from the data as the Fourier transform absolute value squared. So we're just going to have three objects here. We're going to have S, F, and I. That's the only things I need in this part of the talk. So what the Whittle likelihood does is it approximates the maximum likelihood. And here's a discretized form of it. It's sometimes given as an integral. But the idea is that we need the spectral density and the periodogram. And we simply, I don't know if I have it, but we maximize this likelihood with respect to theta to get our maximum likelihood estimate. So it is consistent at an optimal rate, as shown in 83. It can be computed in n log n, because you can use the fast Fourier transform to compute the periodogram. But it's been found to produce significantly biased parameter estimates, even for moderate sample sizes. And I could give about 20 papers here, but I just highlight three: Dahlhaus, Velasco Robinson, and Contreras-Christen, who have found these markedly large biases in the parameter estimates. So what's wrong? Well, the Whittle likelihood function, there it is, once again. Except in the case for white noise, it's well known that the expectation of the periodogram is not equal to the true spectral density of finite n. It's only asymptotically equal. This is because of something called broadband blurring, and if we have a continuous time process, it could also be because of aliasing. And in equations, the reason for that is because the periodogram is in fact a convolution of the true spectral density with something called the fair kernel. Fair kernel here given in curly f, which is the square of the Dirichlet kernel. So basically we're convolving what we'd like the expectation to be with something else, and that gives us a bias. And just to see that in a figure, here's an example from the Matern process. Here's the periodogram, and here's the true spectral density. So we see that especially at high frequencies, we have this large bias. And this bias is leaking into the Whittle likelihood and giving us biased parameter estimates. And that's what we want to fix. So how can we fix it? Well, Dahlhaus proposed using tapering. So that's this object H, which you pre-multiply your data with. You just shove it into the Fourier transform here. make sure you have the right normalization, and then plug it in to the Whittle likelihood. And that does improve things. Velasco-Robinson also proposed using differencing. So you difference your process, first order, and that can lead to improved results for certain processes. And here's an example of that. We're doing better now. So here's a tapered spectral estimate using this taper. And here's our density with and without aliasing, and we're much closer now. But we're still not there. There's still some bias left. And tapering also throws data away, because typically H will be 0 at the tail. So do we really want to throw data away when doing likelihood? So we ask, can you do better? And in a paper under review now, we propose something called the de-biased Whittle likelihood, where here's our regular Whittle likelihood at the top, and here's what we're proposing. So they're almost identical, except F is being replaced by F bar. And what F bar is the expected periodogram. So rather than putting in the true spectral density here, we're replacing it with the expected periodogram given our choice of theta, which is going to be a convolution of the spectral density with the fair kernel, as discussed. So basically we replace F by F bar. So now we're fitting the expected periodogram to the periodogram given theta, and then maximizing over theta. So what that would look like in a figure is basically fitting the red line to the white line. So we keep the periodogram, which keeps all the data, and we fit the expected periodogram to the observed periodogram. And we maximize over theta to fit the red curve to the white curve. But how do we actually compute that in a way that we can still be n log n? Well, before we had a convolution, but a convolution in frequency is a multiplication in time. So what we do is we compute it in order n log n operation using that convolution theorem. So you can say that F bar is actually forms a Fourier pair with the biased autocovariant sequence. So you get the bias from the autocovariance, you get your autocovariant sequence there, and you Fourier transform it. And you have to do a necessary correction there. But it's a simple FFT. So the idea is that we can compute F bar using an FFT and I as well. So now the optimization remains an order n log n procedure, but we need 2 FFTs instead of 1. So it's just hypothetically twice the work. And we can also combine it with tapering. So if you still like the Dalhouse method, it's not a replacement. We can actually do our procedure and compute what this would be the expected tapered periodogram, or tapered spectrum, where here's your taper, here's your tapered spectrum, and this is your expected tapered spectrum. So it's the same idea, and it's still n log n. And we can also combine it with difference. So how does that look in some simulations? Well, here's a Matern process with the spectral density we showed before. That amplitude, damping, and smoothness. We're going to play around with different values. We're going to fix A and C. Somehow their ratios, probably the most important, but vary alpha. So we have different smoothness going all the way from 0.6 to 2.5. Simulate lots of time series. This is all very computationally efficient. And we're going to compare 6 different pseudo-likelihoods. We're going to compare the standard Whittle likelihood and the de-biased one, but also the tapered and differenced variance of each one. So 6 in total. And I'm just going to show you the aggregated results, which is the bias, standard deviation, and root mean square error of each approach. And we basically see that in each case, de-biasing improves the standard approach from here to here, from here to here, from here to here. Especially in terms of bias, standard deviations are all more or less the same. Root mean square error, we can get a significant decrease. And probably overall here, de-bias combined with differencing for this simulation performs the best, but the point really is that de-biasing always improves on the standard approach. So that's simulations, but what about some real data? So here are some ocean drifters, one from each ocean, Atlantic, Pacific, Indian. Here are their velocity time series in U and V. And here are the Matern fits that we get here, which look pretty good, but what parameters would we get using each method? So if here we compare regular maximum likelihood, so the computationally inefficient way, with the debiased whittle and the standard whittle. We don't know the truth, but what we can say is the debiased approach is much closer to the real maximum likelihood than the standard whittle, where we can get some big biases, especially in the slope here. This is where we really spotted the issue, because we're getting the wrong slopes with the standard whittle. The debiased is much closer to maximum likelihood. So it's a really nice compromise between the two methods, because here we see the CPU times where we are a bit slower than standard whittle, but significantly faster than regular maximum likelihood. So we think we've hit a sweet spot between computational efficiency and statistical efficiency. And that's the sort of proof of concept here with some real data. 2 minutes and just some theory. So here are some assumptions that we need to show consistency and rate convergence. And these are all kind of standard assumptions, but the one, and I don't want you to really look at them, because they're all pretty standard. Bounding things, saying your set is compact, blah, blah, blah. But number 4 is the key one, which is that we assume that f is continuous in theta and Riemann integrable in omega. So actually we've been able to relax assumptions from standard literature, because typically they will ask for things to be continuous in omega, in almost all whittle theory. But with our likelihood, we don't need it to be continuous in omega. Riemann integrable is enough. And that's because we don't deal with f, we deal with f bar. And f bar is actually continuous in omega as long as it's f is Riemann integrable in omega. So we're able to relax some assumptions as well. And with those relaxed assumptions, we can show consistency at the minimax optimal rate here, and the proofs in the appendix, where it also holds for these discontinuous spectral densities, which is useful actually in fluids. There's a lot of them. And the key step in the theory is basically the fact that if we look at the score function of the likelihood, then we can see that its expectation for finite samples is 0. And that's what these equations show. It's not in general 0 with the standard whittle likelihood. And that's sort of one of the key steps. And the other one is a lemma, which has been found in other literature as well recently, where we can control the variance of linear combinations of the periodogram. And that turns out to be really useful in showing our rate. So just to sum up, so I want to leave some time for questions. That last paper is under review, and you can download the preprint on arXiv. And then we've implemented that method on the 100 million plus data points in the global drifter program, and those results, that paper's in preparation. And for some future work, we want to extend stochastic models as well as our inference procedures to 3D spatial trajectories. Those exist in the ocean as well as things like bird flight and so on that I was talking about from accelerometer data. We can get 3D trajectories, as well as just looking at other ways of modeling spatiotemporal data like random fields, time-varying random fields, or STS. Yeah, that's it. Thank you very much. And
Well, the debiased whittle had kind of a flavor of maximum marginal likelihood. It's not marginal likelihood, but you are averaging out before you're maximizing.
yes,
Sort of fair.
yeah, that's definitely fair. Yeah, that's a good spot. I'd agree with that. Yeah, you could call it a composite likelihood function, I think, yeah. But I'd rather call it a pseudo likelihood, just because that feels more.
No, but it's probably the right manipulation of the likelihood, the right way to average it. Although I guess it's not with respect to a probability distribution. It's something else.
Mm-hmm. Yeah, that's a good point.
Did I see that you actually reduced the variance at one point in one of your examples?
Yes.
Is that surprising? No, I mean, if you're convolving with something, you expect to increase the variance.
Reduce the variance compared with what was it reduced?
You'd have to go back.
In this set of slides?
Yeah.
Yeah, in the table maybe?
In the table. Yes, here. So in your, if you look at the middle column and the final two lines there,
Yeah.
reducing the standard deviation by biasing.
Yeah, so the rates of all of these are the same. We haven't established which has the better constant or anything. There's no reason to think one would be higher or lower, and that's generally what we find. So in different experiments I show you, it may be that in different cases it's lower and in different cases it's higher. We don't see the method as adding to standard deviation. Alex?
Yes. I was wondering, obviously there is, the data you gather is somewhat seasonal, because the ocean's temperature changes over season. Does this matter at all? Does seasonality change the behavior of the drifters?
Absolutely, yeah. It very much does so. So I didn't show the results here, but if I showed you the temporally evolving coefficients at different spatial locations, you'll see clear seasonal patterns. So when we publish that final paper that we want to do with the analysis of we've got a lot to get through here, which is why it's still in preparation. We'll separate out some of those maps that I showed earlier in terms of seasons. Yeah, good question. Yeah.
So what tapering weight did you use for these simulations?
I was using a DPSS, so Sleepian taper. Yeah. I'd also tried it with cosine taper as well, I think. But
what do people recommend for when people suggest this tapering method for this? What kind of tapering do people recommend?
yeah, so Percival and Gordon will recommend that at least doing a DPSS taper of order 1, because they sort of see that one as almost coming for free. So it's quite a gentle taper, but it gives you a clear improvement. That's for non-parametric. For parametric, using the Whittle, it's questionable whether you need to even taper at all, especially once you use our method to account for the bias. Then you don't necessarily need to taper anymore, but you could.
I try to understand what you did in the first part. It looks to me each model you use is for one float. Then how you fill in this map, you show us very nicely. It looks like you fit several or lots of floats together.
Yeah, that's exactly right. So we fit them separately because this was the choice between Eulerian and Lagrangian that I was discussing. So in this case, we think it's better to be Lagrangian. You fit everything you can for a trajectory, and then you save those spatial locations.
That's not in the equation, it's outside the
Yeah,
equation.
exactly. And then and you do it for all of the trajectories, all 20,000, and then you aggregate that information afterwards.
So for
So
each
you look
given
at-
time, you still can fill in the space in the map.
Yeah, exactly.
Okay.
So through a given point, there may have been 100 drifters that went through, and we aggregate those parameters afterwards by either taking the average or looking at the distribution or median.
But if say the purpose is try to monitor the global warming, you could take another approach for each given location to see how this velocity or whatever change over time.
Yeah, that's a really good question. I feel like we need the program maybe to still be running a bit longer before we can get a track of decadal changes like that. Because yes, it's been running for 40 years, but we've only really had dense data, high-res data for about 15 years. So I think in about 10 years' time, those will be the questions to ask, which is how are these things evolving over a given spatial location over time? Yeah. George?
Richard asked earlier what do you do if one gets washed up on shore, right? One of those drifters, right? And all the plastic garbage is in one of the garbage films, right? Especially the one off the coast of California, right? And that's not the only one. And how likely is it? I was just wondering, is it true that if you wait 10 years or like a certain amount of time that you'll find all your drifters in one of the garbage films?
No, that doesn't happen because plastic plastic by itself will move differently to one of these drifters, and that's the presence of that drogue. One of the problems with plastics is that you have these convergence zones, because what the water is doing is coming in and going down. But a plastic is buoyant, so it will come in and then it will stay there. But a drifter, on the other hand, because it's got that anchor taking it deeper, it'll keep moving, so it doesn't get stuck in convergence zones. Yeah, John?
What else is being measured by these gadgets?
Yeah, so the temperature is a key thing that it's useful for. But they
Ocean
also,
temperature. Or
Yeah.
air temperature.
ocean temperature. But also things like pH and actually ocean color. That's important for biology. So it's literally just the color of the water. But also things like salinity, and some of them will measure wind. The wind just at the surface as well.
They're probably getting fancier as time goes along.
Yeah.
More stuff is getting measured.
Yeah, and there's talk of autonomous ones as well. So ones that you can, because the problem with these is that you deploy them and they freely drift. So you have these black holes, these regions they don't go, but now they're looking at building ones that you can potentially navigate and then let them freely drift, navigate them. So sort of semi-autonomous.
It's a multiple spatial temporal process.
Yes.
In the future, could be high dimensional spatial temporal.
Yeah. All the buzzwords.
Okay, thanks very much, Adam.
Thanks, Richard.